Equilateral triangles today. So this is not the greatest diagram I have ever stolen from the internet, but it would look better if it was in color like it is on my file. But this is a picture of an isosceles triangle. So isosceles triangle, really the only requirement is two of the sides are going to be congruent to each other. That's really the only requirement, which they've got marked in the picture. I just kind of highlighted that with my yellow highlighter. The two sides that are the same are called the legs of the triangle. So in the little diagram, it has the word leg. It's trying to point to this side and this side. Now, this is not really part of the definition. We're going to talk about it today, but I'm just going to write it down while we are here. You also, in an isosceles triangle, will have two congruent angles, and in the diagram those are called base angles. They're what they're pointing to. So you have the two legs. The third side is called the base. The two angles at the bottom here, they're across from the two sides that are the same. Those are the base angles. So now and this is kind of where it's bad. These are a little bit darker color, if you guys can tell. These two angles would be congruent. The two base angles would be congruent. The angle at the top, it's like one of these is not like the other. That vertex angle would not be the same measure as the other two. So the base angles are the same, the vertex angle is not. I do not have any more calculators. Sorry, I just have the one and I got to use it because I'm going to use it on a couple questions here. Okay, now let me draw you a picture here. This is going to just ask you to find an angle, and I'm not drawing this to scale, but I'm going to try to draw an isosceles triangle here. It says the base angles of an isosceles triangle. So isosceles triangle, two sides the same. Base angles are across from those two sides, so it would be those two angles in my little sketch right there. And it says the base angles are both 47 degrees. So this angle 47, this angle also 47. How would you figure out the vertex angle? The vertex angle would be this angle in my little picture that I drew up here at the top. How would you figure out the measure of the vertex angle? Yeah. Perfect. Yep. Just add these up, subtract from 180. Or you could just, if you want, just do 180 minus both of those. And let's see. You got 86? Yep, 86 sounds good. All right, so 86 would be the measure of my vertex angle. All right, now this is a very similar question, but it gives you a little different information. So I'm going to try to, it says the vertex angle of an isosceles triangle is 116. I'm going to kind of try to draw this kind of wide. This is not going to be good, sorry. All right, so two sides are the same here. The two sides across from those angles, or two angles across from those sides are congruent. The vertex angle is, one of these is not like the others, so that would be 116. If I want just one of the base angles, can anybody raise your hand, like how would you go about finding just one of those base angles? Yeah. Good. Okay, so you know the inside angles of a triangle add up to 180. So I'm just going to subtract the 116, and if you do that, we're going to get 64. Now, I got to split that evenly between these two base angles because they're supposed to be the same. And yep, if you cut that in half, you should get 32 degrees. So that would, 32 would be my answer to the question. In my little diagram, it would apply to both of those angles. So just a little bit different math if you have the vertex angle instead of the base angle. Okay, now this is really, I don't need you to necessarily distinguish between the two of these, but I'm going to write both of these down for you today. So this is the isosceles triangle theorem and the converse to the isosceles triangle theorem. So let me start here with just the plain isosceles triangle theorem. If you have an isosceles triangle, you have two sides that are the same. So this says if two sides of a triangle are congruent, then I'm going to write the two angles opposite those sides are also going to be congruent. So if I have two sides that are marked the same in the picture, or maybe they tell me that in the directions, I can automatically have that the two angles, these would be the base angles if we were drawing this, opposite those sides are congruent. So I'm just going to draw a little tiny picture here to let me illustrate this. So basically, if in a diagram, I'm going to try to draw an isosceles triangle. If I had a picture where I marked two sides the same in the triangle, this theorem is going to say then, and pretend I'm drawing exactly the same triangle I just did. I know I'm not doing a good job doing that. If I have that, then you can automatically have those two base angles being congruent. So sometimes they might not mark that in the picture, so you could mark it because of this theorem, which we're going to prove in a second. Now, the converse is going to flip this around. It says if two angles of a triangle are congruent, then the two sides opposite those angles are going to be congruent. So if I have in a picture two angles in a triangle that are congruent to each other marked, then I can automatically have the two sides that are opposite those angles. So if you want a little visual for this one, basically I would have a triangle and they would mark two angles as being congruent. If I had that, then I could automatically put into that drawing that the two sides, one across from each angle, the two sides would be the same. So it's basically, it's a converse. One says I have the two sides, I can have the two angles. The other one says if I have the two angles, I can have the two sides. So that's your isosceles triangle theorem and the converse to that. I'm just going to prove the isosceles triangle theorem to you real quick, actually using some of the skills that we've been using in our proofs. So I have an isosceles triangle here. The isosceles triangle is YXZ. And then I've got a little dotted line in that diagram, kind of it is in the middle of that triangle. I will prove that to you here in a second. So the isosceles part means two sides are the same. So it says in the given information, x to y and x to z are the same. So that's literally the first thing it says in my proof. So that's just going to be given. Now, it also says up in the given information, xb, which is this little dotted line, bisects this entire angle here, yxz. So this whole angle up here at the top, that little dotted line bisects that. So that would allow me to say the next step in my proof, which is that angle 1 and angle 2 have to be congruent. Definition of an angle bisector or definition of a bisector, either way. I'm going to put that little angle symbol in mine. Okay, now, it says in the next step, xb, which is that dotted line, is equal to itself or congruent to itself. That's just your reflexive property. Okay, I'm going to put a little double mark on that. Now, the next step, I'm going to color one of these inside here. It says xby, so that would be this little triangle here, is congruent to xbz. That's the triangle that I didn't color that's just white. So I'm saying those two triangles within that overall isosceles triangle are congruent. Could you give me a reason why the two, like either like the yellow one and the white one? Yes. So you have a side here, angle, side, same thing with this triangle. You got a side, angle in the middle, side. So I would say side, angle, side. Now, if you guys remember from what we've been doing yesterday, we were talking about that corresponding parts of congruent triangles are congruent. So if the yellow triangle and the white triangle are congruent to each other, do you guys see in my congruent statement, y and z are in the same spot? So those are corresponding angles there. So that's going to say angle y and angle z are congruent. That's just your corresponding parts of congruent triangles have to be congruent. That's what we were talking about yesterday. Sure, if you want, that's fine. Okay, now I'm going to show you guys a little, this is just a little problem. I might ask you a question, something like this. So I have this kind of diagram over here to the side, a little bit weird. It says, is AB, that would be this whole side here, congruent to CB? And I'm just going to draw this to the side just to kind of defend this. So I'm going to draw this, but without the little segment from D to E. I'm just going to write ABC. So if I do that, if you guys see in the diagram, angle A has a single curve on it. Angle C has a single curve on it. So I have two angles marked congruent to each other. That actually forces AB and BC, or CB is how they wrote it in the question, those have to be equal to each other. And so I'd say for sure yes, based on the diagram that I have there. It's just a little trickier to see with that extra line. Now, the technical answer to this, I have the two angles, so I can have the two sides. So that's the converse to the isosceles triangle theorem, if I needed to defend that. If you just wrote isosceles triangle theorem, I would be totally fine with that. You can abbreviate all you want. Okay, my other question here is going to involve this little bitty triangle here. It says angle A, and it's asking us if that's congruent to angle AED. So AED would be this angle. I'm just going to, just on my paper, I'm just going to redraw that tiny little triangle to the side just a little bit. So I have A and E, this is D. These two sides, A to D and D to E, those are marked the same. And it also marked angle A. That was in the diagram already. So if the two sides are the same, that does force the two angles there to be equal. Each one is opposite one of those sides. So again, here I could say yes. This one would be the actual isosceles triangle theorem there, because what I have the two sides that forces those two angles to be congruent. If you just write isosceles triangle theorem or abbreviate that however you want to abbreviate that, that's fine. I don't really mind if you are distinguishing between the converse and the actual theorem. Okay, so those are isosceles triangles. Now, I'm going to give you just a couple properties for equilateral, and then we'll kind of put them together.
Okay.
Equilateral triangle. Go ahead.
Isn't it, so you know how we had the base angle, right?
Mm-hmm.
Does that just make the vertex angle the same as the base angle?
Yes, you could look at it definitely that way. So an equilateral triangle means all three sides are the same. That's what I've got marked here. And what that also forces, and I'm not going to mark this in the picture, but if it's equilateral, so all three sides are the same, the triangle will also be what we call equiangular. And all that means is all the angles are going to be congruent to each other. So I'm not going to mark that in the picture, but I will in some of the other diagrams. Just going to leave this alone. But if you have all three sides marked the same, that's going to force all three angles to be equal. And this is kind of the reverse of that. So right next to this picture, I have angle X, angle Y, and angle Z. Those are all marked congruent. If that's the case, if all the angles are the same, that's going to force all the sides to be the same too. So that's going to be equilateral. And that just means all three sides are going to be congruent to each other. Now, what I would tell you though, for the angles, you don't necessarily know the sides unless you have a diagram with some extra information, but you can tell me the angle measures in an equilateral triangle. Does anybody, I know we mentioned this like a while ago, does anybody remember, like, what do the three angles all have to be? Do you remember the measurement for that? No, it's okay. It's got to be 60. You guys know the inside angles of any triangle add up to 180, right? So if I have to divide that evenly between all three angles in the triangle, you could just take 180 divided by 3. So any equilateral triangle, the angle measures have to be 60. You can't necessarily do that with the sides without more information, but you can always tell me the angle measures. Okay, so here's kind of how I'm going to apply this. This is an equilateral triangle. All three angles are marked the same, so that forces all three sides to be equal to each other. What they have labeled in this diagram is the side from O to N and N to P with these little expressions. But if this is an equilateral triangle, I know those two sides, I'm just going to write this real quick, ON and NP, if that's an equilateral triangle, those two sides have to be congruent to each other. So if I want to solve the question, literally all I'm going to do is just put in these expressions. I'm going to do 3x minus 8 has to be equal to 5x minus 40. Completely up to you how you want to solve this. I'm just going to do it real quick. I'm going to try to keep my variable positive. So I'm going to subtract 3x from both sides. And just to save myself some space, I'm in that same step, I'm going to add 40 to both sides. All right, what you'd be left with then, negative 8 plus 40 will give you 32, and 5x minus 3x will give you 2x. And then all I have to do to get x alone there, just real quick, is divide by 2. So if this is an equilateral triangle, x has to be 16 there. If they had said, like, what's the length of the side or something like that, we could plug that back into the expression, but it doesn't ask me that. It just says, what's the value of x? Similar problem. Here, they give me all the sides are the same length, so this is equilateral. That also forces all 3 sets of angles here, or all, not 3 sets, just all 3 angles in that triangle to be the same. What they have marked in this diagram is the angle L is 3x plus 9 degrees. That's it. Can anybody just raise your hand and tell me, like, how would you figure out x in this picture here? How would I figure out x? Exactly. All right, if this is equilateral, it's equiangular. These guys are all 60, so we're just going to take 3x plus 9. That has to be a 60-degree angle. So we're just going to set that expression there. So I would just subtract 9 real quick. That'll give me 3x is equal to 51. And then I'm just going to divide by 3. And x should be 17 then. Is anybody having a question about the equilateral triangles? Okay, I'm going to switch back. I'm going to give you one more property for isosceles triangles here, and then I'm going to kind of put everything together at the bottom. All right, so this is a lot in this diagram. The overall triangle here, I'm just going to outline it real quick with my highlighter. So PRQ, that whole triangle, is an isosceles triangle. Okay, it's got these 2 sides marked the same. Now, we already know the base angles are congruent. That's marked in the picture just from what we've talked about today. But I've got this extra line here, and I'm going to work with this in this problem here. It says if a line bisects the vertex angle. So in the diagram here, this line from R to S, I just extended that a little bit, and it bisects the angle, and I could defend that because on either side of that, those angles are marked congruent. So it bisects that angle. You're going to get 2 properties with this. The line is also going to be, I'm going to write perpendicular, I'm just going to write the symbol for that, is also the perpendicular bisector of the base. Okay, so I'm going to draw in this picture a little bit. The whole base of this triangle, the overall triangle there, would go from P to Q. You get 2 things from that. If it's perpendicular, you're going to get 2 right angles in that diagram. So I'm just going to draw it in the picture. It would be here and here, where that line runs into the base. And then you also get, because of the bisector, 2 congruent sides. In the diagram that I've got right here, it would be PS and QS, which I'll go ahead and just mark, I'll put a little double mark on that. Those 2 sides would also be congruent. So it gives you a lot of information. If you have the angle bisector of the vertex angle of an isosceles triangle, you can get all the parts of the triangle congruent. Basically, you could use a reflexive property and have everything. So basically, on either side of that line, those 2 triangles are going to be identical. So the actual type of problem you guys would have to do would look like what's in example 4 here. So D to B, that bisects the vertex angle. This is overall ABC is an isosceles triangle. This bisects that angle. So what I can have, where that runs into the base, these guys are perpendicular. I'm just going to put that in right away. You also bisect the segments here. So from A to D and D to C, those would be congruent. That's not going to really be in anything we need for this particular problem. What I need in this problem is X. Okay, so a couple ways I could do this. If this is X, this would also be X. Those are marked congruent. If this is isosceles, angle A and angle C would be the base angles. So those both have to be 54. The easiest thing I can tell you guys to do here, if you're trying to find x, when I draw that angle bisector, I actually have two little bitty congruent triangles on either side of that. So I'm going to see if I can draw one just to the side so you can see it maybe a little bit better. So DBC. So this is where x is at. You got a 90-degree angle because you got that bisector. This has to be 54. So all you got to do to find x, any triangle's angles have to add up to 180. Subtract the 90, subtract the 54, the leftover would be 36. So in that diagram, x is just going to be 36. Okay, and then all these questions are going to go with this diagram right here. So this is an isosceles triangle. This line bisects the vertex angle. I can see that because on either side the angles are marked as congruent. So that's going to give me two things. Automatically that's going to be perpendicular. And also on either side of that line intersecting the base, the segments from J to M and M to L, those would be the same. So I'm just putting that in the picture. And let's see, it says if J to L is 10, so all the way across the base is 10. Could you just tell me, just raise your hand, what would the length of the segment just from M to L be? 5. How'd you get 5? Yeah, exactly. So we're just going to cut that in half. So J to M, M to L, both of those would be 5. Okay, now, spoiler alert to I already marked in the picture. So it says find measure of JMK. That's one of the 90-degree angles right here. So this would be 90 degrees. The last thing it tells you is angle LKM. So that'd be this little bitty angle right here is 20. Now, this little bitty angle right next to it is marked congruent, so that would also be 20. And ultimately, what are we supposed to find? Angle J. So you do not have to redraw this. I'm just going to show you on my paper real quick. So angle J would be here, and I'm just drawing the left side of this. So that's 90. This would be 20. So angle J would be right here. All you got to do makes a triangle, so 180 minus the two angles that I know, 90 and 20, the leftover has to be angle J. So that should be 70 for that question. That would also be, I know it doesn't ask you for that, but the measure of angle L would also be 70 in that diagram. And then I have one problem at the bottom. This kind of involves everything we've talked about today. So I've got in the directions, this is kind of a complicated picture, but I have an isosceles triangle ABF. So just right away, what I'm going to do, I know if I have those two sides the same, that forces angle A, and then this angle here, I'd have to call that AFB, or I'd have to give it a number, but I know those two angles automatically are going to be congruent if that's isosceles. The second thing it says right at the top of the picture is CDF. That is an equilateral triangle. So I'm just going to color this on my paper so you guys can see it a little bit better. And if that's equilateral, each of these angles has to be 60. Okay, and then there's one more piece of given information. And this is kind of a weird spot, so I'm going to kind of extend and highlight this. But it says angle AFD. So AFD here, which would be literally like that whole angle, so it's an obtuse angle there, would be 150. So it's just going to ask us to identify what some of these angle measures would be in the diagram. So CFD, that's part of that equilateral triangle. That's just right here. This is 60. So I've already got that in the picture, so I'm just going to write that down. That's CFD is this angle right here, so I just wrote it down. This one's a little tricky. So AFB would be this angle here. How would I figure out this angle here based on what they've got in the diagram?
Would it be right to assume that whatever F is plus 35 equals 90?
Not quite there. I don't have I had somebody ask me that earlier. I don't have a 90-degree mark. It looks like it, but it's not marked that way. How'd you get 50? Yes, this is 55. How'd you get 55? And subtracted it. Yeah, okay, if you guys see this, angle AFD, right? This is this angle, and this angle together. So Zach was saying that he added 35 and 60, or you could just, if you want to subtract the 60, the 35, and this angle AFD have to add up to that, or sorry, AFB have to add up to the 150. So if you want to just subtract 35 and 60, the leftover has to be that angle right there. That should be 55. Now, automatically, I can have angle A, right? Because this is just an isosceles triangle. So angle A has to also be 55, which is actually the very last question they ask you here. So I'm going to go ahead and write that down. The only one I'm missing then, they ask you for angle ABF. So B is going to be the vertex. Angle ABF would be, let me put a triple mark because I put a double mark on that one, would be this angle here. All right, so if you guys look at this, ABF, the triangle, is an isosceles triangle. I know two of the sides. So to get that, an entire triangle has to add up to 180. The two base angles are both 55. If you subtract both of those out, the leftover has to be 70. So that's going to be this angle ABF here as the last question. And then I already knew the angle A from being 55 because of the isosceles triangle. Is anybody having a question? Okay, rest of the time is yours to work on the homework. Please let me know if you need any help. You probably want a